Good morning. Today we will consider the problem of describing the differential kinematics of robot manipulators. I will start with one basic problem that I will draw on the blackboard just for motivating our study. So we have seen that we can describe the geometry of manipulators. So let's take one 3R spatial manipulator, and I will draw it in some particular configuration. Let's say this is the first axis, then I will put the arm in this configuration. Of course, there will be some reference frame. For instance, this is x0, this is y0, and this is zeta 0. And maybe the configuration of this arm in this situation is, let's say, 90 degrees for the first joint angle. And then theta 2 equal, I would say, z 90 degree, let's say, and then theta 3 equal 0. Okay? The robot is not moving, but of course there is no robotics without motion. So we should start moving the robot. How do we move the robot? We apply torques with the motors at the joints, and the joints will start moving. In order to understand how they move, we should indeed need information on masses and inertia, because if it's light, the same torque will accelerate the bodies a lot. If it's heavy, you require more torque to accelerate the same amount each link. But since we are describing kinematics, we don't care about what is the actual source of motion. We just say there is some motion at the joint level, because at the joint is where the actuation occurs. So let's give some velocity. For instance, let's say that this joint is moving with a velocity of 90 degrees, while theta 2 dot and theta 3 dot are being held in the same configuration. Okay? So the differential kinematics required to know what happens due to this motion in the joint space, what happened to the end effector. So we expect that this will have some velocity v, and probably also some angular velocity omega. Okay, I'm writing two vectors here. So our task is to describe this mapping. Of course, this is a very simple case, and just looking at the picture, I could say, okay, is there a linear velocity here at the end effector? How is it oriented? What is its intensity? So this type of question should be asked. Is there an angular velocity here? It's a yes or no answer. So you have 50% of no, yes. Nobody wants to. Well, in fact, there is. Okay. And while this velocity will be in a horizontal plane, so I'm the robot like this. So I will rotate. So I will have this velocity, instantaneous velocity, going in that direction. But in fact, there is also an angular velocity, and this angular velocity is vertical, is exactly along the direction of the angular velocity imposed by this joint, which can be represented as a vector, in the direction of the joint, and its intensity, it depends on how fast I'm rotating. Okay? So we should be, it is always like this. Well, there's another story here. Suppose that we change configuration. Okay? And we put the arm in this configuration. And we give the same joint motion. Now, question. Do we have a linear velocity at the end effector? Everybody's sleeping this morning. I think so. It will be equal to the previous one or different? No. The only answer you give is okay. So let's do the Luca robot. Okay, I'm like this. I was like this. I'm giving the same velocity. Here, the linear velocity, I would say, would be halved if these are equal length. Okay? In fact, if I'm folding this on top of me, on top of my joint, and I'm rotating, there will be no velocity at all. Linear velocity. Okay? So, first consideration, this mapping between a single velocity, even just the most simple case that we can imagine in the joint space, and the velocity at the end effector depends on the configuration. So it's actually it's a nonlinear dependence. But if we froze at the initial instant of time this relationship, so we say, okay, we are in this configuration, I give a velocity at the joints, I have a linear velocity, this is a linear mapping. So if I double the velocity in the joint space, I will have the double velocity. So the nonlinearity is in terms of the configuration of the arm, not on the differential relationship between quantities. Okay? What about angular velocity here? Will I have an angular velocity? How can I state that there is some angular velocity? Well, I just put a frame at the end effector, and if this frame is changing orientation, then it's clear that it should be an angular velocity for that. Okay? In the same way that when I made this example with the end effector on top of the joint axis 1, which means that the origin of the frame was exactly there, so when I'm rotating joint 1, the origin is not moving. This is why the velocity is 0 in that case. Okay? So will there be an angular velocity here? I give the answer, yes. Now you give the answer. Will be equal to the previous one or different? So it will be equal to the situation where I'm stretched. Why?
Because the same degree.
Well, I'll give you it's correct, you're right, it's equal. And the reason is that since I'm taking a picture of the robot like this is a single rigid body. Okay? So when I'm imposing an angular velocity somewhere, and in this case I'm imposing an angular velocity by rotating around the joint axis 1, this angular velocity pertains to the whole rigid body. Remember, linear velocity is a velocity. I mean, we should not even talk about linear velocity. I add this adjective just to make the difference with respect to the angular. But velocity is only of points. So one point may have a velocity, another point may have another velocity, and so on and so on. In fact, when I say what is the linear velocity of the end effector, I'm saying what is the velocity of the origin of the frame attached to the end effector. Okay? So Linear velocity may change depending on the point, but the angular velocity of a body is just one. The whole body has an angular velocity, and that's it. Okay, so it will be the same as before because we are imposing the same type of motion. So you see that the thing is kind of tricky. There are nonlinearity in terms of the configuration. There are linearity when we've frozen the image and just compute the instantaneous velocity, which is what we'll do. Of course, once I have applied this velocity in the joint space for some millisecond, I will change configuration. And then, even if I continue to apply the same joint velocity, I will have another effect on the end effector because I'm in a new configuration. So this configuration dependence will make things more delicate to be handled. Okay? So you're convinced that we need to study this problem, at least from this simple example. So what is differential kinematics? It's the relation between motion in general. We will start with velocity, but we will see that if you want to map acceleration to space, the idea is very similar, and so with higher order differential quantity. So relation between motion in the joint space and motion, linear angular velocity, in the task space, if we want to use this generalized concept, or in the Cartesian space, or more in general of some frame, typically linked to the end effector. Okay? This is the standard definition. Well, this is differential kinematics, and I would say this is forward differential kinematics. So what is the inverse differential kinematic problem? Just reverse things. And exactly like for direct and inverse kinematics, you remember we commented on the fact that the direct kinematics is an analysis problem. I give some configuration, I compute position and orientation of the end effector. Full stop. We have one solution. If everything is correct, no special problem. While the inverse kinematic problem was finding a solution to a set of nonlinear equations. We may find it in closed form, or we need to resort to numerical iterative algorithm and so on. So it's a synthesis problem. We have to find some configuration that realize a specified pose for the end effector. And here is more or less the same, because the inverse differential problem is, okay, suppose that I have the robot in some configuration and I want to have a velocity, say, coming out of the board, of the blackboard. Linear velocity and zero angular velocity, let's say. So what kind of motion should I impose to the joint so to realize this? So it's a synthesis problem as well. And luckily enough, it's simpler than the inverse kinematic problem because we work at the differential level, and for a given configuration, this mapping is linear. So we have to invert a set of linear equations or solve a set of linear equations. Okay? So although the problem appears to be more complex, but in fact it's a bit simpler than inverse kinematics. Okay, and we will see this later on. So, remember, let's talk about velocity, but have in mind in the background that the same thing will apply to acceleration or to the third derivative with respect to time, which is called jerk, and so on and so on. But what we want to do is to compute this instantaneous velocity. This is why I'm saying I'm frozen the configuration and I'm computing this. Then I'm applying the velocity and the robot will change configuration, and then I repeat this. So it's a continuous process. Of course, if you have a computer controlling the motion of your robot, you will command new desired velocity with some sampling time. So every, let's say, 1 millisecond or 10 milliseconds, you command a new velocity. But in our description, which is in continuous time, this is a continuous operation. So the description is instant by instant in a continuous flow. So we will compute this instantaneous velocity, and this is why we can consider for every problem the configuration as frozen, because it's instantaneous. And this velocity, linear angular velocity of the end effector, let's say, can be computed in different way. We will see that. One way is taking the description of the pose, position and orientation, and doing the time derivative. Okay, very simple. So it's time differentiation or derivation. Probably differentiation is a better term then. Okay? We differentiate with respect to time. Time passes. If the robot is not moving its end effector, the velocity will be 0. Otherwise, there will be some expression. Or we can do it in a purely geometric way, which is kind of surprising at the beginning, but really not so much, exactly because we are working with vectors. And so we can make vector operation like vector products or addition of vectors and so on. In fact, when I'm computing the velocity in this simple case, I could just, without differentiation, I just work with vectors. And in fact, I would say, okay, there's some vector omega 1 aligned with the axis of joint 1, because I'm rotating around joint 1. There is some distance vector p to the end effector from the joint axis to the position for which I want to compute this, and then the velocity v will be omega vector p. Okay, this is first course of physics. Okay, and you see that I haven't done any differentiation. It's just geometry of vectors. Okay, so there are in fact two ways for computing this mapping, and we will see that each of these two methods has its own merits or disadvantages. Okay. Unfortunately, the world, our 3D world, is not flat. So there are changes of orientation. And when we follow these two paths, we will see that the rotational quantities needs to be treated in a different way. So, for instance, we need to establish the link between the angular velocity of the end effector and in general of a rigid body and which is a vector, so it's a geometric entity, and something that we may derive by time differentiation of angular orientation. So, for instance, relation with the time derivative of a rotation matrix. The rotation matrix characterizes the orientation. So if this change over time, we know, we understand that there will be an angular velocity. But how do we compute this? Angular velocity is a vector, it's a 3D vector. The rotation matrix is a 3 by 3 matrices, so apples and oranges, or there is some intrinsic relation. So this is what we need to understand. And of course, one may say, well, but why do you want to use the rotation matrices? Why not use something which looks like a three-dimensional vector, like a minimal representation of orientation, alpha, beta, gamma of whatever Euler sequence or fixed axis sequence of angles? Okay? But alpha, beta, gamma of any of this minimal representation is not a vector. Pay attention. You can organize it as an array of 3 numbers, but there is a sequence. So not being a vector, you cannot sum alpha 1, beta 1, gamma 1, and alpha 2, beta 2, gamma 2, because they are computed in different configurations. So Again, you can take the derivative, how this angle changes over time, and you want to map them to the angular velocity. You see that on angular velocity, you have several different choices to make, and you would like to know what is the relation. It's not that you should do like this or like that, or this is better than the other, so we forget about other methods. Sometimes one method is more convenient for doing some computation. Sometimes another method is more convenient, so you want to establish the equivalence and the transformation between the results that you obtained. Okay? So linear and angular velocity. Let's start with a simple example that everybody is familiar with. A rigid body in roto-translation. Okay? So what do we see here? The Earth is moving. So if I take a picture at some day in the fall, it will have some linear velocity as a body in the space. Okay? But it's also rotating around the sun, and so there's a revolution and there's a rotation. So it spins in 24 hours around some axis, which is typically inclined with respect to the elliptic of. So you see that there is everything here. It's a rigid body. It's not really a sphere. It's a geoid, as you know. But when it's rotates, suppose that in the near future there will be no more season. So this is impossible, likely, but the Earth will stop going around the sun, so it will stay always in a fall day, okay? And then day and night. So it will just rotate around some axis. So we can have an angular velocity. What is the angular velocity of the Earth in this situation? If we froze the seasons, 0. Makes one turn in 24 hours. So I would say 360 degrees in 24 hours. Or not. Okay? It seems very slow. In fact, it's slow. But if you live in Rome, Rome is, I take this picture from Rome is there, or if you live in Rio de Janeiro, or if you live on the equator, then the linear velocity of object there, it's quite large. Why? Because the same omega is when you consider points, the distance to the axis of rotation will give you more linear velocity with the same amount of angular velocity. Okay, so all points of the Earth have the same angular velocity, but if you consider specific points, they have their own linear velocities, or velocity, just like this, depending on where they are. And there are also points that have 0 velocity. Which ones? Exactly those who lie on the rotation axis. So on the surface, the poles. Okay? Clear enough? Good. So this slide, we will skip it right now because we have commented. But just keep it in mind. And it's a kind of a small proof to state that the angular velocity of a rigid body, for instance the Earth, or for instance link 7 of the lightweight robot, and so on, or the gripper of an industrial robot, it's something that pertains to the body, not to a specific point. Okay? And this comes out of the fact that we are considering rigid bodies. So we cannot deform these bodies. So we have a kind of a fundamental kinematic expression that tells you if you know the velocity of some point of this body, let's say point pi, and you know the angular velocity of the body, then you can compute the velocity of any other point of this body. Okay? In fact, if you don't have angular velocity, so the body is only translating in space, then all points of the body have the same velocities. Why? Because this is 0. So Vpi equals Vpj for any ij. Okay? If you take some point that has 0 velocity, still other points may have non-zero velocity because there is an angular velocity. This is the case of the Earth rotating on its axis on a fixed day in the year. Okay? Unless the new point has a distance from this one which is orthogonal to the direction of the angular velocity. Okay? And this says that if I take the Earth and I take the pole has 0 velocity. Okay, so all points on this axis have 0 velocity as well. Why? Because the vector going from the pole to one of these points, which is internal to the Earth up until you get out of at the South Pole, have a position vector Rej, which is aligned, sorry, I said orthogonal, which is aligned with omega, so the vector product is 0. So cancel orthogonal from recording. Okay? So this is important. Keep this in mind. Well, I should say, why the rigid body constraint is important? Because if the body is rigid, no matter how you move it around, the relative distance between 2 points is the same. Cannot change. You cannot stretch or compress. It's a rigid body. Which means that while you're moving this body, all points have velocities, but these velocities have some constraint. They cannot go like this, because otherwise the distance would extend, or like this, because otherwise they would compress. So the velocity can only be orthogonal to the joining points. For instance, here, you see that this point P3 has some velocity Vp3. This point P1 has some velocity Vp1. Okay, so if I compute the relative velocity of the two, this should be orthogonal to this distance, so that the segment P1, P3 can move around but cannot extend. Okay? This is behind all this very simple slide, but very significant one. Okay, so now what is our situation? This is a typical slide that I use. A chain of body connected by elementary joints. The bodies are rigid. The joints can be only of 2 types, either revolute or prismatic, and now we know this very well. And then when I'm giving some velocity to the joint, which means I'm giving a scalar value, 90 degrees per second, or if it's a prismatic joint, 10 centimeters per second. Okay? But in fact, this scalar value has a direction because it occurs along or around the joint axis. So in fact, it's a vector that I can build from that. Okay? So for instance, if I'm giving a velocity to joint 1, and this is revolute, it's like imposing an omega 1 vector, which has the direction of the joint axis, zeta 0, and then an intensity theta 0.1. a scalar, okay? And similarly for the other, for instance, for the third prismatic joint in this chain, its axis, instantaneous axis is Z2. It has some orientation depending on what are the value of the joint variable that precede this joint. And if I'm giving velocity to this joint, I have a D3 dot. Remember, D3 is the variable of a prismatic joint, so this is what can have a variation over time. And this is imposing a linear velocity, not an angular velocity. It's a prismatic joint, V3. And all this contribute to linear and angular velocity of the end effector, as we have seen there, depending on the current configuration and, of course, on their intensity, because their current configuration specify the orientation of the joint axis in space at that time, and then the intensity of the motion will give a contribution to the end effector. Okay, so we have made there a situation where only one joint was moving, but in fact, you don't need to do this. You don't need to move like a zero generation robot that moves first one joint, then the other, then makes this. Okay, all is coordinated, simultaneous. And the nice thing is that because of the linearity of this mapping, you can work by superposition of effect. So you look at what is the effect of omega 1 on V and omega of the end effector. Then what is the effect of omega 2 on the same quantity and of V3 on the same quantity and so on. And then you superpose all the effect and you have the result. Okay? Of course, in the given configuration, you would have a completely different results if you impose the same scalar velocities at the joints in a different configuration. Why? Because the joint axes are different, and so they contribute in a different way to the linear and angular velocity of the end effector. Now, when I'm saying linear and angular velocity of the end effector, it's a handy way for saying the velocity of the origin of a frame attached to the end effector, the last frame of the Denavit-Artenberg convention, and the angular velocity of the end effector as a body, or equivalently, of the frame which I attach to this rigid body, which is changing orientation. Okay? So, since these are vectors, I represent these vectors with starting from the origins of that frame. But remember, while V is the linear velocity of that point, omega is, I mean, I'm just for convenience, I'm putting it there, but it's the angular velocity of the whole frame of the whole body. Okay? Now, when I'm doing direct kinematics, I know that the pose of the end effector frame can be represented either by a homogeneous transformation matrix, which contains a rotation matrix for orientation and some position vector for the position of the origin of that frame, or from there I can extract some task variable r, which may contain, in this case, the vector p for the position and the minimal representation phi of the orientation, which is extracted from the rotation matrix R. Okay? So, this is what I said before. Pay attention, because while V and omega are really vectors, so they belong to a vector space, or in algebra this is also called linear space. So they, if you sum them, you don't have any problem in ordering, whatever comes first, and the contribution can be, for each joint can be summed in this way, no matter which is the sequence. Well, when you take phi and and phi dot, or d phi over dt, well, then this is neither this nor this are vectors. Okay? So remember, they can have a time derivative, but this is not, they cannot be treated as vectors. Okay? Why I'm insisting on that? Because this, unfortunately, gives a lot of problems in practice, and also from the educational point of view, my experience is that all students have some difficulty at the beginning, so I'm trying to go slow on these things. So, take-home message, omega, the angular velocity, is not the time derivative of a minimal representation of orientation. There is a relation, but we need to work a little bit to take it, to obtain it. So, and why is this, there is this difference between linear quantities and angular quantities? I haven't said anything about linear quantities. In fact, when I take the position p of a point and I take the time derivative of this, so p dot, this is v, the linear velocity. So, no problem. Why there is so much difference between the two things? And the explanation is here. So when you're considering only translations, then it is not important the order in which you do this translation, let's say along three axes which are orthogonal. No matter if these translations are finite, so delta, or if they are infinitesimal. Okay, so if I'm moving first in this direction by 1 meter and then in this direction by 1 meter, is exactly the same final solution as if I'm first moving in this direction and then in this direction. Okay, and this is true both for finite motion and for infinitesimal motion, which is what is of interest when I'm talking about velocities. Okay? Same final position, so the sequence doesn't matter. Now look at this. We know that finite rotation do not commute. Okay? This is one example. When I used to smoke, I would take out my packet of cigarettes with a brand on it, so now this is no longer the case. So I start from an initial orientation, and I'm imposing some rotation, finite rotation. Let's say I want to rotate first 90 degrees around the z-axis, so this box reaches this position. Okay? And then, in the sequence, I want to rotate 90 degrees around the x-axis. So this positive counterclockwise when you put your head on the arrow and look at them. So this is the final orientation. What if I'm flipping the two things? So first rotate 90 degrees around the x-axis. So the box goes there with the arrow just for nice view, and then I do the rotation around the z-axis, 90 degrees around the z-axis, counterclockwise. This is the final orientation, and as you can see, they are different. And this, we know already that we cannot exchange the order of rotation, okay? But this has an important mathematical fact. No, I'm talking about finite rotation there, but the reason why I'm getting to the different orientation is linked to the fact that the angular velocity that I'm imposing, because now I'm giving just a finite rotation, I don't specify time. I'm not saying in how much time do you do this rotation. I'm just saying this is the result of the rotation, this is the result of the second rotation, full stop. If I'm now putting time into the picture, so I will have some angular velocity, well, the angular velocity is not an exact differential form. You remember this concept from calculus. analisi 1. So this means that if I want to integrate the history of the angular velocity, and integrating the history would give you some information of how your orientation has changed from some initial orientation to a final orientation. So I'm starting with some orientation. I have some angular velocity history. If I integrate what is this history, I will get the final orientation. This is what I would expect. Well, this is true, but this depends on the path of integration. So on the sequence of how my vector omega changes over time. If it changes only around one axis, then no problem. Okay? So in general, finite rotation still commute when made around the same fixed axis, but otherwise this is the picture. And I will make a simple example here which mimics what you see here on the So suppose that you start from some orientation at time 0. This is time now. This is the orientation of your rigid body. And now you give this history of omega. This is time. Suppose that this is omega x, this is omega y, and this is omega z. Suppose that you want to rotate by, let's see, at the speed of p over 2 radian per second, which means 90 degrees per second, for 1 second. And then you stop. And then the motion ends at time 2. While you want to not have any angular velocity around y for 1 second, and then have this one. Again, pi over 2. While omega z is always 0. Okay? So this is the story of omega. So I can say, look, what is the integral of omega tau? Is a vector. So integrating a vector means integrating the single component. Okay? So this is can be decomposed in 2 parts. I hope that everybody agrees with this. And then from 0 to 1, this part, the result, 0, 0, and then it's the integral of this. Okay? Which is for 1 second pi over 2, so it's pi over 2. Okay? Same thing for the other. Well, in the second interval, this is 0, so this will give no variation. And the area here is the integral between 1 and 2 of pi over 2, so it's 1 interval of time times p over 2. So these are velocities, so they can be added. So this is pi over 2, 0. Okay? So if I had some initial rotation and applying this story, this will give me some variation of orientation there so that I move to r of 2. x, y, so this is not exactly, because here I have made x, z, but I mean, you can understand that it's very similar to this situation. Now, if I take another story, of omega x, omega y, and omega z, t, and I say, okay, I don't want to move for 1 second around x and then I apply an angular velocity of pi over 2 for 1 second, and I do the reverse here. So this is pi over 2, 1 second, and I don't move here for the whole interval, and I compute the integral of this new profile. I obtain exactly the same results, but I know already that I reversed the rotation, so I will end up with a different orientation, which means that which one is correct? Well, you cannot just take the final results, depend on the path of integration. The fact that you have done first a velocity around some axis, so it's the history. I think that everybody now is convinced, I hope. Okay, so what about now infinitesimal changes of orientation? This is quite interesting because this is a computation that we should do together once in our life and then forget. Or better said, then not forget, but not do it again. Okay? So what does it mean that I'm doing infinitesimal rotation? And I'm taking elementary rotation around the 3 axes x, y, z. So if I'm making a rotation by an angle, a finite angle phi x is a scalar, around the x-axis, I know that the rotation matrix has this form. Okay? Now if phi x is not a finite amount, 35 degrees, but it's small enough, so it's a delta d phi x, then I can approximate in Taylor series sine and cosine and stop it at the first order because second order and higher order term are so small that can be neglected. And this is what I obtain. So this is the rotation matrix around the x-axis due to an infinitesimal angle delta fx. Everybody agree with this? So I'm replacing cosine around 0. This expansion around 0 is 1, then blah, blah. And then times the increment, which is 0. While sine is replaced by the angle. Sine of delta phi is replaced by delta phi. Okay? And I can do the same for the other 2 elementary rotation matrix. So from finite to infinitesimal, I have this type of expression. Okay? Now pay attention. If you remove the identity, so the diagonal one, all these are skew-symmetric matrices. You see this? Okay. Now, let's do the following. Now, suppose that I want to make the concatenation of these 3 infinitesimal rotation, and I take one order. So let's do the natural order, Rx dfx, then Ry dfy, then Rz dfz. And I want to compute the results. So this is this first product. Now so first row, 1, 0, 0 times first column gives a 1. Then same thing for the second, 0, and then d phi y. Then second row of Rx df, so 0, 1 minus df times this gives dfx dfy, the minus sign cancel, times this gives a 1, times the third column gives a minus d phi x. And finally, last row of Rx, 0 dfx1, multiplied by the first column gives a minus dfy, multiplied by the second column gives dfx, and multiplied by the third column gives a 1. And then we need to multiply this by the last matrix. And we got the final result. Okay? So let's do it. Now, first row times first column gives a 1. First row times the second columns gives a minus d phi z. So this one takes this one and the other is 0. And then first row times the last columns gives a d phi y. Well, pretty good, huh? Very simple. Now the second row is much more complex. This row times this column gives dfx d phi y, then plus d phi z, and this is the first element. Then second row times second column gives a minus d phi x d phi y d phi z, so this times this, and then there's a 1, and then that's it. And finally, second row, last column, just takes a minus d phi x. And now last row is this product times first column is minus d phi y plus d phi x d phi z. Then second time this one gives d phi y d phi z with the plus sign, and then plus d phi x. And finally, and this is easy, just a 1 here. Huh? This times this. Okay? Oof, never again. Now, we have said that these are infinitesimal quantity, which means that this is a second order quantity that is practically 0. This is a third order quantity that is practically 0. Same here for a second order quantity, and same here. So what is left is this matrix, and if you're very diligent, you can at least try another sequence and do the same simplification that we have done on second and third order infinitesimal terms, and you will see that no matter which is the order, you obtain always this matrix. Okay? Which is, again, the identity matrix plus a skew-symmetric matrix built with the increments d phi x, d phi y, d phi z, as if they were a vector. Okay? So this can be written, in fact, as identity plus skew-symmetric matrix built with this vector. Okay? So the result is that infinitesimal rotation commute, and since from infinitesimal rotation you get, if you divide by time, by delta t, you take the limit for delta t going to 0, you get omega, and so omega is a vector, in fact, because the sequence is not relevant anymore. Okay? I think you're convinced about this. Okay, this is already what I wrote on top of this. Now, omega, now we have made this distinction between finite and infinitesimal linear translation or angular rotation. Now let's take a representation of orientation with a rotation matrix. So R specify the orientation of a rigid body. What if this is changing over time? So what if, suppose that I have a frame which is represented by R, its orientation is R, and suppose that this is doing, let's do it like this. This is so I can put here R of time, and this is the orientation of this frame at time t. So at time 0, what is this orientation? I've given some time dependent. I could have put here cosine of t square, whatever. No, I'm doing now that. So what is the value of R of 0? The identity. What is the value of, let's say, instance pi over 2 omega? Pi over 2 omega is, so I removed omega just for convenience. So cosine of pi over 2 is 0. Sine of pi over 2 is 1. There's a minus 1 here. And there's a 1 here. There's a 0 here. And this is. So this is the orientation. So what happened to this? If this was x, y, and z, at this instant, how is my frame oriented? At time t equal pi over 2 omega. Now remember, what are the columns? They are directional cosine of the x, y, and z axis with respect to the initial frame, which is the identity. So this means that x is now oriented like y, which means that here is x prime. If this is r prime, okay. This is how the y is oriented. So this is y prime, and of course z prime remains like this. So at this time, this has made this rotation. And then what happens? It continues to go in that direction or not, or just comes back? When time passes by. Well, I don't care now, but at least I've given you an example of something which changes over time so that it makes sense to compute r dot, which is the velocity. It's not the velocity, it's the time derivative of the rotation matrix, which represents an orientation. So it should be linked to the fact that there's an angular velocity there. Okay? Now this is, in this case, is very simple to do this computation, but now we will do this in general. Okay? So let's have a rotation matrix, which is a function, a generic function of time. I don't want to look inside how it is made. I was just to check if I can give an expression for its time derivative. Okay? And for doing this expression, I use this very simple property. I know that the rotation matrix is an orthonormal matrix, so its inverse is R transpose. So when I do R times R transpose at any time, I will get the identity. So this is true. So if I have this relation which holds always, I take the time derivative of both sides. So I take the time derivative of the identity is 0, doesn't change. And then I take the time derivative of the product R transpose. So I'm going very slow. So the time derivative is the differentiation with respect to time of the product RT. So this is a product, so I take the derivative of the first term times the second not differentiated, and then reverse. So I take the derivative of R with respect to times R transpose, and then plus R, the time derivative of R transpose with respect to time. Okay? Now I look at this is a product of two matrices, R and some matrix which is the time derivative of R transpose. I don't know how it is done, but now I can switch them and transpose. Okay? So this expression is like having the two reversed transposed and take the transpose of the product. So the R becomes the second matrix with the transpose. The DRT dt becomes the first matrix transpose, so the transpose is eliminated, and then I transpose everything. And now what I see, I have a matrix, dr dt times R transpose, plus the same matrix transposed, and the result is 0. So I can say that this product inside the square bracket is a skew-symmetric matrix, because it's a matrix that if I sum to this matrix is transpose, I get 0. Okay? So, first conclusion. This matrix is skew-symmetric, and I call it S, and I call it S of time. I don't know how it is made, but I know that it's a skew-symmetric matrix. Do you agree with that? If you take a skew-symmetric matrix, which, if it's a symmetric matrix, if you sum it, you get twice the same matrix. If it's a skew-symmetric, you eliminate the matrix, okay? So, and now, remember the Earth spinning. So suppose that you have a point, and this point is fixed in a frame R, which changes over time. So the position of this point changes with the position, with the orientation of the frame. So this point has a dependence on time, not because it's moving in the frame, so its position is p prime, it's constant, just because the frame is changing its orientation. Okay? So constant norm means that this vector, is always the same. So this is a frame, there's a distance from origin, so it changes, but it doesn't expand or changes orientation inside the frame. Now, take the derivative of this, time derivative. So you have p dot or dp over dt. I'm using this notation just to make very... So I take the derivative of this. This is constant. This is time dependent. So I have drt dt times p prime. But I know that since this product gives a skew-symmetric matrix, I don't know how this skew-symmetric matrix is made, but so I can multiply, plus multiply by R, and I have that the derivative of R is S of t times R. So I take this and I replace it by S of t times R itself. I see some... Did I lost you? It's clear, this passage? So I have this one, this identity. Then I plus multiply by R, so I have this is equal to ST times R, because this is eliminated. So here I have the derivative of R, so I replace it by S times R. And now I recognize that this is my original vector. Okay, so I can say that the velocity of this point is this matrix, which I still don't know how it is made, I only know that it is skew-symmetric, times the position of this vector. Okay? Now, look at this wonderful trick. So what are we making? Well, it's clear that there was some frame, there was some point in this frame, and this frame was rotating around some axis with some velocity omega. It's like the Earth is spinning around its north-south pole axis. Elementary physics says that the velocity of this point is omega vector p. So p dot is omega vector p, but we know that this vector operation can be replaced by a product of a skew-symmetric matrix built with the component of these vectors times the vector p. So these two expressions are the same, these two expressions are the same, and lo and behold, this means that ST here is S of omega. So it's the skew-symmetric that can be built with the angular velocity. Let's put everything together. And we have this relationship. Depending on what you are looking for, we started. What is the time derivative of a rotation matrix? R dot is SR, where S is the skew-symmetric matrix made by the component of the angular velocity. So if I give you an angular velocity and I have a rotation matrix, I will know what is the time derivative of this rotation matrix just by doing the product of the skew-symmetric matrix with the omega times the orientation of this frame. Or reverse, if I give you the time history of the rotation, so R dot, and I want to say what was the angular velocity of this change of orientation, then I reorganize things. So I isolate S of omega. So I post multiply by R transpose. And I have R dot, R transpose is S of omega, which means give me the rotation matrix as a function of time. I take the derivative of each element with respect to time. So I have R dot. I multiply by the transpose of this matrix, and I'm sure that I will obtain a skew-symmetric matrix. And if I look inside, there will be the component of the omega. Here is an example. Again, very simple example. It's complementary to this one, just to make sure that we touch ground. So I have an elementary rotation around X, which means, okay, what will be the final results? What will be the omega when the element of this elementary rotation are changing over time? It will be an angular velocity which is oriented like the x-axis, because I'm rotating only around the x-axis. So I already know in advance the result, so that I can apply the formula and check if this, in this simple case, everything works. Okay? So I know that I want to compute the omega, so I use the relation S of omega equal R dot R transpose. So I take this R, I take the time derivative. So time derivative of 1 is 0. 0 remains 0. Time derivative of cosine of phi, it's minus sine of phi times phi dot. I'm not saying how phi of time changes. I say whatever it is, it's sine of phi times phi dot, and then I can take phi dot outside. And similarly, derivative of minus sine of phi of t with respect to time is the derivative of minus c with respect to phi, and then of phi with respect to time. So phi with respect to time is phi dot, and I take it out, and this derivative is minus cosine phi, and so on. Okay? So this matrix with this scalar factored out is R dot. Then I multiply by R transpose, so pay attention, I need to transpose that matrix. I do the computation, and without any simplification, pay attention, it's not like there, I obtain this matrix. It's skew-symmetric, 0 on the diagonal, and opposite element on the off-diagonal term, and I know that this is the x, y. This is the z component. This is the minus y component, and this is the minus x component, sorry. Minus z component, minus x component, y component of the vector. So I extract from this the vector generating this Q-symmetric matrix, and I find that what is the angular velocity is some vector oriented like x with intensity, the intensity phi dot. Okay? It's clear, this example? So I'm not giving a specific form. Here I've given a specific form of dependence to phi of t. I said phi of t is a linear function of time, which is omega, a factor, time t. I can do the same for this. Okay, exactly, you can do this by for exercise. Just follow these steps. Okay, not enough mathematics today. This is even harder, I would say. Okay, now we have put in relation the derivative of a rotation matrix with the angular velocity omega. Now let's do the final jump. We have said omega is not the derivative of a minimal representation of orientation, no matter which this is. So what is this relation? So let's put in relation the time derivative, for instance, of RPY angle and omega. So again, what are we doing? I'm saying I have an orientation represented by three angles. This is one example. And these three angles change over time. So this means that the orientation is changing, and if the orientation is changing, I should have some angular velocity. What is this angular velocity? Okay? So, first step. So remember, now we want to make a sequence around fixed axis, x, y, z. So this is a roll pitch yaw. Fixed axis type of sequence. So first an angle alpha x around the fixed x-axis, then an angle b of y around the original fixed y-axis, and then an angle gamma z around the original z-axis. Now, it's much more practical to look at this in the equivalent form of a sequence of rotation around moving axes. You remember that. Each of the 12 standard sequence around fixed axis is equivalent to another of the 12 sequence around moving axis. You have to reverse the order and exchange the angles. So RPY alpha beta gamma is z y prime x double prime. So I've changed the order of axis. First it was x, y, z. Now it's z, y, x. But now the angle are computed around the moved axis after the first rotation and after the first two rotations. And the order of angles are reversed. Okay? You remember that. So if now I'm giving a history to this, the colors are hardly recognizable, but the alpha is blue, the beta is green, and the gamma is red. So I'm now, the first operation that I'm doing is I'm giving a change of the angle gamma around the first axis. So this is gamma, and now this is changing over time. And if this is changing over time, this means that there is some angular velocity which is oriented like the z-axis, because I'm rotating around the z-axis. And if it's a big vector, it means that I have a lot of speed there. If it's a small vector, I have small speed. If it's zero, I have no rotation at all. If it's negative, I'm rotating clockwise and not counterclockwise, and so on. Okay, so this vector represents the change over time of this angle, which is the first in the sequence ZYX Euler type. Okay? So this will give some contribution to the total angular velocity. Now, the second angle, beta, is a rotation around the resulting y-axis after the first rotation. So the first rotation brought x to x prime, so y to y prime, and now I'm rotating around this axis by an angle beta. And now I'm changing the speed of this rotation. So I'm going faster, or so a longer vector here, or slower. So I have a b dot which is aligned with y prime. And then the last angle, alpha, is around the resulting x-axis. So this was after the first rotation. This is after the second rotation. And now I'm giving an angle around this x double prime. And then I'm changing the history of this angle. I'm giving more or less speed. So I will have an angular component of an intensity alpha dot, which is aligned with x double prime. Now you see that I have three vectors, the red, green, and blue, that I have to sum, because each of these represent an angular velocity, okay? Which is a function of alpha dot, beta dot, gamma dot. But they change in time, because I'm not looking at fixed axes. This depends on the beta and the gamma angle. Pay attention, not on the alpha, but on the beta and gamma angle. So now we will do this computation. So these three contributions, green, red, and blue, will be summed, and this will be the resulting angular velocity associated to the sequence of time derivative alpha dot, beta dot, gamma dot. Now this requires some geometric view, but at least for some component this is simple. So look at this. I'm organizing this as the three contribution. I have to sum this vector plus this vector and this vector. The intensity are given by alpha dot, beta dot, and gamma dot. Now I just need to find the direction. How is this vector directed? How is this vector directed? How is this vector directed? In a generic orientation given, specified by alpha, beta, gamma. This is why I'm organizing this table in the form of a product of a matrix times a vector. This is not really a vector, but this is a vector, okay? So, and now I have to put here the columns. So let's start with a simple one. Gamma dot is along this direction. Which is this direction? It's always the same. It's always along z, and z is fixed. So I expect here a 0, 0, 1, and in fact this is what I get. Okay? 0, 0, 1 is the contribution of the vector of intensity gamma dot aligned with z to the total angular velocity of this reorientation. Now the second contribution is beta dot, is along this axis. Now y prime is in the xy plane, so it's because I'm rotating around z and I'm bringing y to y prime. So I expect that this vector will have a 0 here, and then this angle actually is this angle. So if I do the right computation, this is what, this is the unit vector in the direction of y prime. Pay attention, these are always unit vectors because their intensity has been taken out with the scalar alpha dot, beta dot, gamma dot. Okay? Can you see it? If you cannot see it, there's another way of doing this systematically. So what have I done after the first rotation? I've done a rotation around the z-axis. Okay? So in that product, this rotation matrix, the second column of this rotation matrix represents what? The directional cosine of the y-axis after the rotation. So the directional cosine of this. So you just build the elementary rotation matrix RZ with a gamma, take the second column, and this will be the second column. So this is algorithmic. Here it requires to look at the geometry, trigonometry, and so on. This is algorithmic. So the last contribution will be alpha dot along this x double prime direction. So this will, it's pointing in space depending on the two angle beta and gamma. It's not so easy to see how it looks like, but this is the result. Okay, and if you don't believe in that, you should make your computation. So what is x double prime is the unit vector along the x-axis after the first two rotations. So I do my first rotation by the angle gamma, then a second rotation around the moved axis y prime, represented by an elementary rotation around the current y-axis by an angle beta. I do this product, and then this is the x-axis, so I need to take the first column of this because I'm looking at the x-axis, and this first column is exactly this one. Okay? So, lo and behold, now I have some magic relation between what? Between the time derivative of this sequence of angles, so of a minimal representation of orientation, and omega. And you see that this is not the identity. So it's true that omega is not phi dot when phi is alpha, beta, gamma of any sequence. This is just one example. Of course, one could build many more. So this matrix, T, I will call it T, has nothing to do with the homogeneous transform. You can call it whatever you wish, but it's referring to, well, we made this transformation, but actually we were interested in the derivative of the three-angle alpha, beta, gamma of a roll pitch yaw sequence. So I'm writing roll pitch yaw like there. And you see that if you're doing things around fixed axis, this matrix depends only on the second and third angle, will never depend on alpha. Or if you wish, if I'm doing this for that Euler sequence, z, y prime, x double prime, this matrix does not depend on the last angle, alpha. Okay? So it depends always on only two angles. The first two in a moving axis sequence, or the last two in a fixed axis sequence, just because of this equivalence. Okay? Now, this matrix, is it singular or is always non-singular? Why do I ask? Because if it's non-singular, then give me an omega, I will give you the alpha dot, beta dot, gamma dot of your representation by inverting this matrix. And vice versa, give me alpha dot, beta dot, gamma dot of any of this, and the associated T, I will compute omega. Now, if we compute the determinant of this matrix, it will never be always non-singular. It will always have some singularity. The determinant in this case is cosine of beta, which means that when beta is plus or minus pi over 2, this is singular. And then pay attention how you read this. Still, you give alpha, beta, gamma dot, you can compute omega. But if I ask you a synthesis problem, give me your sequence of speed of angles that produces this omega. And I may not find a solution in that case. So there are some omega that cannot be represented in this way. Okay? When the representation is in singularity. And if you go back to this inverse problem of minimal representation of orientation, you will find that the Euler sequence z, y, x, when the second angle beta is plus or minus pi over 2, produces no solution. It's not able to specify all the three angles. So we call this a singular cases, but in fact it's singular because the differential mapping, which is connected to a matrix, has a singular matrix in that configuration. Okay? So this is very important. This is the so-called singularity of the RPY representation or of the ZYX Euler angle representation when we're moving axes. We know that this is equivalent. Okay? Well, this is one example. You can generate the same thing in other example. You can find among the exercise, the written tests of exams, a couple of this example. So I use this just as a check. Okay, so we are done with this. Now let's become operative. Okay, we have mentioned that the mapping between, because what we have said was just representation of angular quantities and mapping between omega, r dot, alpha dot, beta dot, gamma dot, and so on. Okay, now we want to go back to the manipulator and compute the mapping between joint velocity and effector velocities, whatever they are. And we can do this in two ways, as I anticipated at the beginning, either by performing time differentiation of a direct kinematic map or by considering geometry. Okay? And geometry means directly working with linear and angular velocities. So the first way is pretty much simple. Suppose that you have some task variable, r, as a function of the joint variable q. In particular, you can consider this the classical case, so where you're using as a six-dimensional r vector with the three components of the origin of the last frame of your manipulator, and with three angle phi extracted by the rotation matrix of the direct kinematics. Okay? Now, you take the derivative of this. So, r dot will be p dot and phi dot. Pay attention, this is not omega, but who cares at this stage? So, this was a function of q. Q is a function of time because I'm giving velocity to q. So, I will make the partial derivative of f with respect to q and then of q with respect to time. And you recognize this. We have already introduced this Jacobian matrix when we consider numerical method for solving inverse kinematics. And we said we need this matrix, and this will be useful later on when we do differential kinematics. Here it is. Okay? So this is a matrix. In this case, it's 6 by n, because I don't know how many joints are there. It's a 6 degrees of freedom robot. It's a 6 by 6 matrix. It's the Jacobian of the Kuka lightweight arm, which has 7 joints. It's a 6 by 7 matrix. It's the Jacobian of the SCARA, of a SCARA robot. It's a 6 by 4 matrix. Okay? Remember, the Jacobian is just partial derivative with respect to the joint coordinate, not with respect to time. This is the matrix. And you factor out the velocity. So this will be a function of the configuration. If you froze the configuration, so you're taking a picture and you're saying, okay, this is the configuration of the arm, I'm giving joint velocity, what happens to the end effector? Between q dot and r dot, there's a linear mapping because this matrix becomes a matrix of numbers. So all the nonlinearity are frozen inside the Jacobian, but instant by instant, it's a linear mapping at the difference. So this is very important. So you can imagine that also inverting this mapping is inverting a matrix, or pseudo-inverting a matrix if the matrix is not square. Well, what is instead the other Jacobian that we will consider, the one that does not involve any derivative? This is called a geometric Jacobian, so a geometric approach. And without doing partial derivative of anything. It's just said, okay, I want to have linear and angular velocity of the end effector. So I will have some Jacobian without an R, because I'm not referring to a particular kinematic function, times Q dot. And this matrix can be partitioned in two, the linear component and the angular component, the first 3 rows and the last 3 rows. It's a 6 by n matrix, always. It's always a 6 by n matrix, because these are two 3-dimensional matrices. Omega is omega, and V is P dot. So the upper part, if there is the same P dot, will be equal to the upper part of the analytic Jacobian if I'm using as task variable this task variable. But remember that this is always fixed. This is uniquely defined, because these are uniquely defined. But when I'm using the task approach, in the vector R, I can put whatever I wish, even not at all P dot. I can put some task variable that I need, and I will have my analytic Jacobian. So this is something completely different from the geometric Jacobian. Okay? I'm now making this analogy only if here I have also P, so P dot is the velocity. Phi dot is not omega. So, okay? So again, this is always a 6 by n matrix. This is a m by n matrix, where m is the number of task variables that I'm considering. It can be 1, 2, 7, 180, whatever. While this is always 6 by n. So, and now, let's do a computation for our good friend, the planar robot, 2 joints, 2R planar robot, and let's compute the one possible analytic Jacobian. Depend on what are the variables that we are interested into. For instance, we are interested in the coordinate px and py of the end effector, and on the absolute orientation of the frame attached to the end effector. So since this is planar, the only change of orientation is around the z-axis. So we just need one angle for describing orientation in the plane. Okay? So this is the direct kinematics. The first part is the well-known, and also the last part. Using the Denavit-Artenberg angle, Q1 and Q2 are actually here theta 1 and theta 2, exactly those of the convention of Denavit-Artenberg. So this is the direct kinematics. The sum of Q1 and Q2 is just the orientation of the end effector. And now we take the derivative in order to compute the mapping and the analytic Jacobian. So remember, this is the way in which I present it here, but you will never do this. So here I'm taking the derivative with respect to time. So I take this expression. Let's just read one of this. So this is px time. So I have L1C1. So I take this partial derivative with respect to Q1, and then Q1 with respect to time. So the partial derivative is minus L1 S1, and then Q1 dot. And then I have the second term. This depends on Q1 and Q2, and both Q1 and Q2 may change over time. So I take the partial derivative with respect to Q1, and then the partial derivative with respect to Q2, and the partial derivative with respect to Q1 will then be multiplied by the derivative of Q1 with respect to time, and this will give minus L2S12 Q1 dot, and the partial derivative with respect to Q2, which is exactly the same, will be multiplied by the time derivative of Q2 with respect to time. So, in fact, you can work all together as minus S12, L2, and then the sum of the angle. Okay? So this is the mapping, but it's not in the nice form. The nice form is, I hope I have it. Well, is this one. So I just need to compute the Jacobian, because I know that this Jacobian multiplied by Q1, Q2, full stop, will give px dot, py dot, phi dot. And here I'm taking the same expression and I'm only doing partial derivative with respect to Q1 and Q2, because I know that the linear velocity q dot will be factored out. In fact, I can factor them out from here and organize this relation as a product of a matrix, the analytic Jacobian, time q dot. In fact, so once I've done this the first time, I just forget to make time derivative. I just take the direct kinematic and I made partial derivative of this with respect to the q. And this will be the Jacobian. And then this Jacobian multiplied by q dot will give r dot, full stop. Okay, it's clear enough? You see that here, for instance, for this element, I have q1 dot here, here, and stop. So I take whatever is factoring q1 dot, and it's this term. And then I have q dot here, so this term is in the second column. Okay? So this is the way in which you do computation, even symbolically. If you have this symbolic expression, you can do partial derivative with respect to symbolic variable q1, q2, and so on. And this is what you need to build a symbolic expression of the Jacobian, like the one that I've written by hand here. Okay, let's take a break.